So then, jumping ahead to the end of the last video, what we kind of derived at the end of that was the momentum conservation equation, right? So rho d dt v equals the divergence of the Cauchy stress plus rho b, right? And remember this notation, d dt is what, right? It's the material time derivative. So if we wrote this out all the way, right, it would be like rho dv dt plus v dot grad v is equal to like that. And we might, in additional notation, like that. So that's just, it's all the same. And it's where we ended last time. So if it wasn't clear, I mean, if you remember the Cauchy stress, if it's not clear, and that's one of the reasons I wrote it out in additional notation, this is a little x here. This gradient operator here is a little x, right, with respect to a little x. Right? So it's like little x, which means this equation is really only valid or lives in what configuration? Current or deformed configuration, right? Because remember, the Cauchy stress relates forces in the deformed configuration to areas in the deformed configuration, right? So let's sort of draw a picture of that. Right? So we have the current or deformed, right? Current configuration. We have some little area ds and some traction vector t, normal vector n, all in the current configuration. And then we have this Cauchy stress equation that we derived. It's this, right? Okay? But areas in the current configuration are a little bit, well, let's say, I was going to say weird. They're not weird. They're just inconvenient for solid mechanics. Because in solid mechanics, one of the things we know really well are areas, line segments in the current configuration, right? We have a piece of material, we can go out and get a ruler and measure it before any deformation occurs, and we know that really well, right? So it might be more convenient to work with areas in the reference configuration, okay? And so if we draw the reference configuration, right, and remember we're going here with some deformation. If we look at, well, let's do this. Let's say that T in the current configuration, T times ds, T is a traction or is a force per unit area. If we multiply it by the little area ds, then we have a force, okay? So this is dF, and that's equal to T ds, okay? So let's draw that force, that same exact force. It's the same exact vector, okay? Has identically the same components in the reference configuration, right? So here we have the same dF. It's a vector. Well, we have a little area D now, big S, okay? We have a normal vector. We'll use a big N here, right? Keeping with our tradition of capital letters in the reference and lowercase in the deformed. Okay. Now, again, we have this equation in the current, right? Now, would you agree that there's some traction? There's some traction vector, just like I have df equals t ds. Would you agree that down here there's some traction vector in the reference configuration that when I multiply it by the big area gives me df, the same vector? Right? So there's some traction t, right? There's some traction t that when I multiply it by d big S now gives me df, where the two df's are the same, right? There has to be. It's just a vector multiplication. I mean, this is just, right? I mean, it's just, the big T is df divided by ds, right? Has to be. Right? So I know the area in the reference configuration, ds. If I divide df, which is my force in the current configuration, which I just superimposed on the reference configuration, right? And I just divide by that area, that gives me some traction T. But the tractions aren't the same. Okay? The tractions aren't the same, the df's are. And the ds's we measure. They're areas. Okay? So, just like we had T equals sigma T in, we could also say that there's some relationship, there's some tensorial relationship. Remember, we just derived this first equation with geometry, right? And we could do the thing, I'm not going to go through it all, but we could do it all over again in the reference configuration, right? And what we would get would be some tensor, I'll call P net right now, times this. I mean, we just get the same relationship. Okay? So what we're after is sort of, ultimately, is maybe a relationship between the Cauchy stress and this new thing I haven't given a name yet, okay? But clearly a tensor. All right? But in order to get there, one of the things we'll need is a relationship between the unit vectors. So we know, let's write down a couple things we know. We know how arbitrary little vectors transform, little vectors, right, transform between configurations. They transform like this, right? We also know how volumes transform, right? So dV transforms under J dVO. And here's the one time I'm going to break from the tradition of using capital and small vectors, this and density, right? Because there's really no capital density, so we use rho O to represent the, there's no such thing as like a capital, density. They would look the same, right? So we use the symbol rho O in the reference configuration, and we're going to do the same thing here. Of course, there's a little v and there's a big V, but they look so similar, right? I don't want to confuse you. So in the reference configuration, we'll use the subscript O for the volume, right? And J is the determinant of F, right? Or the determinant of little x, big X, right? It's just a coordinate transformation. And we use that in the conservation of mass that was in the videos, right? Okay, so these two things we know. All right. So let's write down the volumes dV as a dot product, right? And the dot product is going to be of some little ds transpose dx, right? So the volume where this is like it's a surface vector, right? And I'll say what that is. It's d little s, is equal to the scalar ds, this is my area in the current configuration, times the normal vector, right? So this surface vector is just the area times its normal vector, okay? And likewise, I'll have a ds vector in the current configuration, which is d big S times n. Okay? So then I also have dVO is equal to d big S vector transpose d big X. So if I take these two equations and I plug it in here, right, then I get that ds transpose dx is equal to j d s big S transpose dx. Right? And then now I have a little dx here, but I have my deformation gradient equation, right? This guy. I can plug it in right there so that I get ds transpose f dx equals to j d big S transpose dx. So then the dx's I can cancel on each side of the equation, and I'm going to write the next step here. But I'm just going to solve for, so I have ds transpose, this is little s, is equal to j d big S transpose f inverse. And I got to that by multiplying this equation down here on both sides on the right by f inverse, right? So if I multiply f inverse here and f inverse here, this is f times f inverse, which is the identity matrix. So that term just becomes ds transpose, right? And then I just want to get rid of the transpose. So I'm going to take the transpose of both sides of the equation. So I have ds is equal to j f minus transpose, so inverse transpose ds. So this is how those areas, remember again, in ds is just the area times the normal vector. Yeah. Is it okay to what? You mean put it here? Yeah. I took the transpose of both sides, right? So you got to be really careful with matrices, right? So on this, I multiply on the right by f inverse, which gives me f inverse, which is the identity matrix. So I have ds transpose left. That's what I have here. And then I have j ds transpose f inverse, okay? So that's what I have here. This is identically what I have here. Now I'm going to take the transpose of both sides of the equation. So ds transpose transpose is ds, okay? And then this is just a scalar. There's no such thing as a transpose of a scalar. So it's the transpose of this quantity, right, which is the transpose of each of them reversed. So I have ds transpose transpose, which is ds, and f inverse transpose, which we write this little shorthand notation. So this is, you can't just, this is the equation. This is called Nanson's relation.